Donc je vais faire la présentation en français puisque Haysam comprend le français. Donc c'est un très grand plaisir aujourd'hui d'accueillir Haysam Telib, dont le parcours illustre de façon particulièrement remarquable le dialogue entre modélisation physique, simulation numérique et méthodes issues de l'intelligence artificielle. Il a été formé à l'université de Munich, il a ensuite mené une thèse à l'interface de la mécanique des fluides au Polytecnico de Torino et de l'acoustique à l'École centrale de Lyon, consacrée à l'optimisation aéroacoustique des hélices aéronautiques. Il a poursuivi ses recherches dans le cadre de stages postdoctoraux à l'Université de Bordeaux, au Polytecnico di Torino, et également une collaboration avec Boeing, je crois, autour des techniques d'accélération d'optimisation aéroélastique. Ce parcours est à la fois scientifique et industriel, donc il l'a conduit très tôt à se situer au croisement des questions qui sont au corps de notre séminaire. Comment exploiter au mieux des modèles physiques complexes, comment réduire le coût de calcul, comment faire de la simulation un véritable outil d'analyse et de décision. Depuis 2010, Haysam a joué un rôle majeur dans le développement d'Optimad, une entreprise italienne spécialisée dans les solutions avancées d'ingénierie, la mécanique des fluides numériques et surtout le Reduced Order Modeling. Depuis l'intégration d'Optimad au sein d'ESTECO en 2024, ce dont il va sans doute nous parler, il accompagne le développement des activités d'ESTECO dans le domaine de l'intelligence artificielle explicable, du deep learning, des approches hybrides associant données, réduction de complexité et simulation. Son titre est donc « Between Physics and Data, a Critical Examination of AI Role in Simulation-Driven Product Development ». Et ça rentre donc particulièrement en résonance avec les thèmes que nous explorons dans ce séminaire Maths-4-Innov-Action. C'est donc un très grand plaisir de lui donner la parole aujourd'hui.
Thank you very much, Yvon. So, good morning, everybody. I will talk in English. First of all, I would like to thank you that you came and that you found the time to listen to my talk. So, today you have to pardon me, because this talk is very different from the talks that I usually do to industrial stakeholders or even to academia. Because normally when I talk to academia, I talk about a lot of technical questions, about barriers that, for adoption of reduced order modeling and things like that. Today I want to do something very, very different, and so this is why I have to put my hands in front of me. I really want to provide you, or try to provide you, a heads up on what is happening in the community. As you can imagine, also in our community, which is about simulation and things like that, it is now AI here, AI there, AI all around. So it's only about AI. And of course, there's an intersection between AI and what you're learning in this seminar, which is the part of the exploitation of data. We'll see that there are major differences, technical differences, but I think it is important really to understand the context that we're living in. Because dynamics changed a lot over the last few years, as you probably also experience in your everyday life. So this is why this title, Critical Examination of AI's Role. As you probably already understood from my CV, I'm very much into optimization, shape optimization, in order to, in the product development phase. So we're talking a lot about mechanical engineering, and where the adoption of simulation tout court has become a de facto standard. So everyone employs simulation to optimize their products. Reduced order models, AI, still don't have a clear role, but this we want to examine exactly this. So, because there are, of course, other use cases of reduced order modeling. For example, optimal control, or maybe you had a past lecture about digital twins and things like that, but I won't touch this point. So I am saying that in order not to also to create confusion, because one thing is optimization, another thing is, for example, a digital twin or optimal control. They're two different things. Okay, I have a lean agenda, a small introduction, which will actually take, I think, the biggest part of the talk, talking about physics and data and some conclusions. So, what are we actually talking about? Because in optimization, I mean, numerical optimization has been around now, I don't know, for 20 years. Shape optimization in order to define the shape of your car that minimizes drag. This is quite a standard thing. But when it comes to optimization, by definition, there's also always a functional associated to the problem. For example, in this case, we want to minimize drag with some constraints. For example, there should be space for the passengers, for the drunks, and things like that. Otherwise, it would be a trivial problem. And data-driven models have always been a part of optimization, because in optimization, you normally employ, for example, response surface methods to accelerate the optimization process. So what are these response surface methods? They're, in the end of the day, they're interpolation methods, which take a set of parameters as input, and they give you a number, one number, as an output. For example, you parameterize the car, the length, the width, the shape in your CAD system. You have your set of parameters. You throw it into your simulation pipeline, and you calculate the drag. And so you have on the input side your CAD parameters, on the output side the drag. And this has been around for decades now. Today, what we're focusing on are all the other methods that are capable to reconstruct the full answer. That means the full flow field, for example, if we talk about fluid dynamics. But of course, at a fraction of cost with respect to this simulation. So this simulation, I don't know, it costs you 100 CPU hours. A reduced order model, it takes you a fraction of a second if it is well designed. And you don't get just one number, you get the entire data that is associated to your solver. That means the surface pressure, the velocity field. You can do the post-processing whatever that is necessary to your problem. So the first thing is now, when does it actually matter? So we said there were methods around RSM that accelerate optimization. So when do I actually need the full flow field? That's the very first question that we have to answer. So let me start from this one here, full order insights. So we said that, for example, we could calculate easily the drag with a simpler method. But, for example, designers, they don't rely just on one number. They inspect exactly the whole flow field because they have that experience. For example, they want to see the separation, where it occurs, how big it is, in order, for example, to estimate only the acoustic answer. So in a lot of use cases, it just does not boil down to one number. Even though there is one important number, there's a lot of stakeholders around that need to know more. And with a reduced order model, you can give them all the information that they need, that they are used to from their simulation. But there's maybe something more important. The input space for a reduced order model, or broadly for an AI, could be non-parametric. So, as you saw, as I said before, these response surface methods, they rely on the fact that there is a parameterization, a set of parameters that define the shape of the car, and you get the output. Now, in principle, in a reduced order model, this is not strictly necessary. You can derive a reduced order model where you don't know anything about the parameters. You want to know the drag of a new car. You provide, for example, the surface mesh or the mesh related to that new car. You evaluate the residuals associated to your reduced order model, and you can estimate the flow field without knowing anything about the parameterization. And this is a use case which is very, very important to the industry, because we'll see later, there's a paradigm which is called push right, where the industry wants to exploit historical data. So, for example, you have all the simulations of all the cars that you did in the past, and you want to exploit this data set to estimate the aerodynamics of a new car. Of course, a new car cannot be expressed with the old parameters that you used 10 years ago. It's a completely different geometry. Still, there's an opportunity to exploit these data that you generated maybe 5 years ago for a different model, because there is no intrinsic necessity to have a parameterized problem. Finally, which is probably the main driver in the aerospace industry, and you see already things differentiate. The car industry, transport industry is something, aerospace is something completely different. You see, aerospace, and again, Fabien was already here or will come, I don't know. Okay, already came. Aerospace, for example, is intrinsically a multidisciplinary problem, whereas in automotive, it is not the case. In solving a multidisciplinary optimization problem is something really, really expensive. Because if you want to do it with an RSM, in order to get your database, you have to have multiple realizations of the multidisciplinary system, which, of course, implies iterations among different disciplines. So if you want to create an RSM, you have to solve the system several times by changing the parameters, and then you have the data in order to train the RSM.
RSM means?
Response surface methods. So you build an RSM of the entire aircraft. Whereas with reduced order models, you have the opportunity, for example, to create a reduced order model for the structures, a reduced order model for the aerodynamics, and iterate among the reduced order models. And you have this possibility only with the reduced order models, because in reduced order models, you get as an output the full domain. So, for example, let's say domain 1 is our aerodynamics. You get the entire loads over the wing, the entire load distribution over the wing, and you can exchange that load distribution to the structures to deform the wing. The deformation of the structures will give you, by solving the structures, you get the displacements of the wing, and you will update the shape of the wing to resolve the aerodynamics. And so you can simulate complex system of systems with a much lower budget than with classical methods. And this is the major driver in the aerospace industry. And so, when it comes to the product development, these are actually the two use cases. Or you have either the necessity of full insights or the necessity to couple different domains. Okay. Now, let me tell you two stories from my career. So, when we founded Optima, which I was one of the co-founders of in 2009, and in 2011, we were actually called by the phone, which is already strange, by the purchases of Lamborghini. They found us via our website because there was a lot of things about aerodynamics and optimization there. And so they called us. And they were saying that they will open up a tender because they want to do an innovation process on their aerodynamic optimization approach in the company, which was based on trial and error. Okay. So we were already very happy about that phone call that they considered us, and but what we did, we get into touch with the let's say the technical ownership of that domain, that were the engineers that had the task to optimize the shapes of the Lamborghinis. So, so we got to know what they would do up to date. We asked them about, for example, the HPC infrastructure that you have. What is it? How much does the solver take to do one evaluation of the aerodynamics around the car? And we saw very rapidly that they would not just need an optimization software because it was the least of the problem. The problem was that with the HPC infrastructure that they had at their disposal and the cost of the simulation, they could not afford even to explore the design space. It was simply too much. They would say that what they would typically change in the car shape, and there was no way of doing it. And so from there, a very technical discussion started, and we said, look, some of us in our PhD developed something which is called the reduced order models. With that in place, maybe we can cover that gap in order to enable you with that infrastructure, starting from that solver, which was OpenFOAM, to build up an infrastructure for aerodynamic shape optimization. And in the end, they would trusted us. We won the tender. We got mad in developing this. But it was really a technical discussion. With your peers at Lamborghini, there's this need, that solution, we could probably do it. I mean, to a certain extent we did it, to a certain extent we were not able to do it. But this was something that happened, let's say, more than 10 years ago. Last year, I was already working for ESTECO. One of our customers, through our sales network, came in contact with us and said that they were looking for data-driven solutions. Okay. And so they put me into the loop of the discussion. So the company, it's a top 500, Fortune 500 company. I cannot disclose the name. And the guy presented the problem to us, and we said, okay, fine, but in the end, you don't need much. With this and that, it should be doable. And the guy said, okay, nice, but I want to use pins. Pins, I don't know, are physical informed neural networks. Okay, you want to use pins, but you see, apart, I don't know if they will work. But you see, it's like an overshoot, like something. No, and I was trying to convince him that with really small modifications on what they're doing, they could solve their problem. So, no way, I want to use pins. But how comes it that you want pins? And he confessed that it boiled down from the C-level management. So the CTO of a multi-billion company said, which this company doesn't do anything about simulations. They are manufacturing goods, mechanical goods. Said he wanted to use pins. You see, and this is a completely different conversation because it's not a conversation with your peer. And so, looking at this, you see, I came across that slide here. That slide I mean, it's a slide. I mean, we don't want to go into the content of that slide. There are people who are saying about the evolution of data-driven things. You see here ROMs, geometric convolution, pins and things like that. Either a huge adoption or not so huge adoption, but that's not important. The only thing that is important is the author of all of that. It's McKinsey. McKinsey that has an opinion about ROMs, pins, geometric convolutionary networks. And you see, and again, because it's McKinsey who talks to the CEO, to the CTO. And so, just to tell you, everything is changing. Even the dialogue between us and our peers is changing because there's a different dialogue, a different stream of information that takes a completely different route from the top to the bottom. And so, why does McKinsey talk about pins and ROMs and things like that? It's about this thing here. These are investments in startups, in capital investments, in simulation-related AI, so reduced order model, geometric deep learning, and things like that, in millions of euros from 2010 to now. This is an estimate, but this is last year. So last year, 4 billion euros have been spent by venture capital in investments in startups in AI around simulation. 4 billion euros. Now, we'll see afterwards what it exactly means. But as in the best crime stories, you have to follow the money in order to understand. So what is happening right now, and why is McKinsey, it's not just McKinsey, all of them are interested in AI in simulation. So let's have a look on the history. So the very first years where we have been part in, we were talking about reduced order models. So reduced order models, often we were talking about POD, some linear encoders, plus the solver, the residuals, to find exactly the solution in the reduced space, plus some data-driven approach. But as I said, today I don't want to go into technicalities. What is important in our piece is that we would be able to do this kind of solve this kind of problems. You see, there's like the same car that is deformed in millions of ways. But there's an affinity between all of the cars, all of the shapes. There are no topological changes. There are no additional parts. It is actually just a morphing of a baseline geometry. And this can be actually solved with a reduced order model. So in that period, what is important is this second part here. The training data that is necessary to build your ROM is generated for a specific task. You want to do an optimization. For that particular optimization, you build your a database as big as possible, as small as necessary. Well, you understood. As small as possible, as big as necessary, to get the job done. But this data set will not. The lifespan of that data set will end with that task normally. People are not capable of reusing it on. And what it means in talking business, it is a paradigm which is called shifting left. That means you try to anticipate high fidelity simulation, costly simulation, as early as possible in your design cycle. Anticipating is easy. I mean, it's just making it at the disposal of everyone who wants to use it. But, of course, the more people use high-fidelity simulation, the more you will spend in HPC and licenses and things like that. So the real objective is anticipating left, make high-fidelity simulation at the disposal of everyone without making the cost explode. And this is the role of the reduced order model. The reduced order model is there in order to keep the cost under control. But you can do it from a certain point onwards, because you see, for example, these are variations of the same car. If we cannot employ this kind of technology in the very beginning of the design phase, where we have very strange design variants. But the good thing about that technology is that it is very, in a certain sense, it is very parsimonious in the data consumption. So typically 50 data points, 50 snapshots, 100 snapshots are good to bootstrap, but the bad point is that it is very intrusive. You have to go to the source files of the solver, and it is also very complex, which in today's world is really a problem. So this was the first wave where we were one of the major players around mid-2010. Then there was a second wave where we also played a role there, which was around deep learning. And so the mantra became reuse historical data. So for example, that image here, it was generated by Gemini, by AI. But it is exactly that. You want to give to your customers something in the hand which can resolve the flow field over all of those cars. With the typical technological stack of a reduced order model, that would not be possible. You have to do something else. To do that, you have to rely on, as I said, on deep learning. But what now becomes very, very different is the lifetime of the data. Now we're not talking about data that is generated on the fly. Now we're talking about data that is stored by the company all the time. Every time a simulation is run, that data is being stored. As you can imagine, this brings a huge complexity on the management of the data. But in principle, through geometric deep learning, you can come up with a technology that can predict you the flow field around all these different shapes of the car. Now, let's talk about the most interesting part now. What is happening in the last few years? In the last few years, there is a push about really substituting the solver. So it's not that I give you the technology to train a model that can accelerate something. The trend is I give you at disposal a pre-trained AI model that can substitute entirely your solver. The technological stack behind it, it's the same thing as before. We're talking about deep learning, transformers. But what has changed completely is the business model. So here we're talking like ChatGPT, but on simulation. Pre-trained model that you probably adapt a little bit with a small set of your own data. But now, what is, of course, very different is that the training data is not yours anymore. It's the data of the guy who builds the model, like ChatGPT. And where does all this money go to create that data? So, to give you some numbers, let me go back one slide. So, we said last year there have been deals around $5 billion in venture capital. So, the entire simulation market, so if you sum up of all the revenues of everyone who's selling simulation software, is $9 billion. So this investment is half of the market size. You imagine how huge it is. And if you think, I mean, you said, okay, 5 billions, maybe they financed, I don't know, 1,000 actors. No, they're less than 10. Yeah. And so this money, if the size of that money, with respect to opportunity, if you think of someone who was really well-funded, like Tesla, this is 5 times Tesla. The money that these guys receive in proportion to the market is 5 times Tesla. You see, there's an incredible push. And this is why McKinsey is talking about that. Now, as I said, if you want to understand, you have to go back, you have to follow the money. So where does this money come from? Who's putting all that money in that? That's the answer that makes you, that's the question that makes you understand everything. This money comes from chip manufacturers. 30% of that money comes from NVIDIA, ARM, Intel, Applied Sciences. The game that they are playing, it's to use a word that is a little bit in vogue, sadly in vogue, it's actually a proxy war. It's a proxy war on hardware supremacy. And we're playing it for them. Yeah? So, and this is why now, you see, for example, us in ESTECO, we always reinvested our earnings in innovation, but there's no way of computing it, of competing to that. No way, no way. So, and this is what also, I mean, I've always worked in industry, for industry in my career. But what makes me sad is that this is going through without any barriers. And even often in the academia, you see, people follow just blindly these trends. I mean, I understand that it is difficult to block that trend or to fight against it. But it is really happening. We cannot do much about that. And yeah, so this is a little bit for my introduction in order to make you understand, let's say, the ecosystem that we are moving in today. In fact, when Yvon invited me, you see, I'm very bad in titles and things like that. I wanted to call that presentation "Innocence Lost," but because it's like that. It has become something very different. It's not about scientific curiosity. I mean, for us who are facing that world, the conversation is a completely different level. Okay, now, I mean, I'm running out of time. So let's talk a little bit about this data and physics. So, because if you go around to the industry, as I said, at a certain point it comes up, why don't you use physics-informed neural networks, or everything is physics-driven, physics-informed, physics-aware, and things like that. But just to fix a little bit the nomenclature, the physics. Okay, everything starts normally from a solver, from any kind of solver. And already normally in that solver, data played a role because there are a lot of coefficients in the models that has been calibrated to some experiments. Okay, but this is, let's say, we keep it aside, and this. In the classical reduced order model community, in an offline phase, data is generated using that solver. That data is used to determine a reduced space that afterwards we're going to move in that reduced space, and we'll try to find our solutions there. But how do we find our solution there? Normally, there is a modified solver, that means the cousin of that solver, that help us to determine the exact solution in the reduced space that we're looking for. So here, really, when we go online, again, the solver is involved. Then, of course, there are millions of variants on that. It can be the solver plus a machine learning part or whatever. But at the heart, there's the solver. Then there are full data-driven approaches. Again, for the training, we generate a lot of data. But now, in order to move in our online, when we have to do predictions, it is based on machine learning somehow. And we'll see that there's a major difference between these two guys here. And now, the physics-informed neural networks. You see, in a physics-informed neural networks, actually, you're training a machine learning model where, for training purposes, you use normally a different solver. You cannot use this solver, you use a different one. Why do you use a different one? Because this solver has to be integrated in the machine learning framework, like PyTorch, TensorFlow, and things like that. It is nearly impossible to include a legacy solver in this kind of frameworks. So you normally introduce another solver. And this creates a lot of headache, because this is a different solver with respect to one that you normally use to generate the data. And you create a discrepancy. In fact, in a lot of physical informed neural networks, there are two parts. One related to the solver, another one to the data, and you have to weight them. But at the end of the game, it's a neural network in prediction. So when it comes to prediction, no physics, no residuals normally are involved. And you see, the fact that here you use a solver, and here you have the data, some people, and I disagree on this, it's something completely different. No, in my opinion, it's not something completely different, because you see, residuals and the data of the realization, you can see that the residuals are just an implicit representation of your data. What is your data? The data are all those points where the residual is 0. So these two guys here are actually, in my opinion, cousins. One thing, of course, if you have the solver involved, you can rely also on, let's say, on the neighborhood where the residual is not exactly 0. So for example, you have a measure on the distance with respect to their training data, which is the residual if you do it correctly. But in some sense, you could do that also here. You could, for example, train also with not completely converged solutions. Why not? In a multi-fidelity setting, you create a baseline of a lot of solutions where you don't converge to machine precision, and then you create a smaller subset of data where you converge to multi-precision. And this is why, me personally, I'm not a big fan of that, because in my opinion, it introduces a lot of overhead that is not worth the game. But of course, a lot of people would disagree. Okay, so let's have a closer look to those two guys here. Now, the residuals. As I said, in ESTECO, we slowly moved away, we had to move away from reduced order models to fully data-driven approaches. Why? The first one is really structural. As I said, if you want to build a reduced order model, you should have access to the solver. And to many solvers, you don't have access to. But then there's another aspect which is even more complicated, the availability of data. The availability of data is, so you see, it's a little bit hard to interpret, I see, but this is the residual of what is called a converged solution in aerodynamics. And you see, in reality, there are a lot of zones where the residuals are very, very high. We had to clip it. There are orders of magnitudes. So in reality, this solution is not converged, but it's an industry standard. It is done like this. We cannot argue that. The solver does not converge. It takes maybe just one order of magnitude. In their experience, that is enough to correlate, and okay, this is the data that we have. But now, if you use this as a solution to a reduced order model, you have to deal with that, with those spurious oscillations in the residuals, which is a tricky task, because at a certain point, you have also residuals which are due to the fact that not that you're away from your solution, simply because you don't have the correct solution. You could argue, okay, but the reality is that the physics here is, for example, transient. They try to resolve it with a steady state solution, which is impossible. You should solve the transient. And in fact, for example, industry is starting doing that. We're moving away from, for example, Reynolds average, Navier-Stokes equation for aerodynamics, and people do less. Large ID simulation, I don't know. It's some better technique that results a lot of more scales, and it is more accurate. But no one will store the entire transient. They will store the averaged results, because in the end, they would want to know what is the average drag or the average pressure. Not Why? Because there's a storage requirement between the average and the transient, which is 3 or 4 orders of magnitude. So you simply don't have the data. And so, at the end, it boils down to this. Nor the badly converged steady-state solution, nor the averaged results are solutions of the solver. And this is tricky to deal with. Okay, now I'm really running out of time. There's also something else about the residuals, but pardon me, I'm going to skip this because I have 4 more minutes and I should conclude.
No, you have more time.
Really?
Yeah, you have a quarter of an hour.
Quarter of an hour? Yeah, anyhow, I will, let me check. What do you have to talk about? Yeah. I will skip this because this is going really technical about the residuals, things like that. Let me move to this one, especially. So, at a certain point, I said that there's a major difference between reduced order models and fully data-driven models. So, now, imagine you have a very, very coarse computational model. That is, your solution space is of dimension 3. So you have 3 grid points. Okay. You have 3 grid points, and your solution space is U. And so here we plot the solutions in that space. And imagine you have your problem has 1 parameter. So you do you have a value for that parameter, mu1, and you create a solution which can be represented there. You do that several times for different values of mu, and you move around like that. And these are our realizations. Yeah. Okay. Fine. So, what is the solution manifold? Not the solution space. The solution manifold are all the points, all the loci, the trajectory that these points occur when we change mu. So, on these points, all of the solutions of our parameter space mu are located on this. Here, we have just 1 parameter, so it's a line. It's of dimension 1. If we had 2, it would be a hyperplane, and so on. This is the solution manifold. Especially students get a little bit confused with it. So, okay, until now, we didn't introduce anything about reduced spaces, reduced anything, nothing. Yeah? It's just our solution manifold. So, at a certain point, we can say, okay, let's find a reduced space, in our case here, a plane, because that embeds well that curve. That means the distance of all of those points to that plane is small enough for doing something. So, okay, now we introduced a reduced space. Okay, here in dimension of 2, we did not gain much. We went from 3 to 2, but it is, so what is very important now? You see, in doing that, I'm introducing that plane here. I could, as you see, I could do it without knowing anything about the parameters. The only thing that I need to know is the solutions. And I could determine that plane just out of the solutions. Whether this is parametric or the value of the parameters, I don't care. It is just a subspace such that my realizations are not too far away. And I was not obliged of using the parameters. And as you probably saw, at the end, this is the core of a reduced order model. That space here, because now we went from 3 to 2, but normally you go from 10 millions to 10, and you have to determine where on that plane your approximate solutions look like, where it is. So, and you use the residuals in order to go as close, but sorry, I'm moving too far. Yeah. So we project our solutions on the plane, and we can represent the projected manifold in our plane. So now, when we solve a reduced order model, we try to get as close as possible normally to that yellow curve, the projection of the manifold into our reduced space. And in order to get as close as possible, we exploit normally the residuals, because we said what is behind of that is that if I'm close to this real solution, also the residual will be small in a certain norm. Okay. Now, I can do something else. Now, I could start saying, but why should I do all of that? I could directly approximate the solution manifold, the projected solution manifold. And I could, when I want to go from here to there, I could, for example, use a first order approximation on the projected points. And here, this is the point where everything changes, because in order to draw that line here, you need to know where to start and where to end. You have to know about your neighbors. And in order to know about your neighbors, these must be labeled data. That means that you have to know that, for example, in this case, the value of our parameter, here it is smaller than here, and here it is smaller than that. So, in order to build a data-driven model, the parameterization, either a priori or posteriori, is crucial. You cannot build it without it. So, in data-driven models, you're not really you're not approximating the solution space, but you're approximating the manifold. And in order to express a manifold, you need a parameterization of that manifold in order to move around on that manifold. And what does this imply is that if the dimension of that manifold is large, you need a huge amount of data. If that dimension of that manifold is 20, that means you have 20 parameters to describe all of your variants, your geometrical variants. You will need millions of realizations. And this brings us back to what has been said before. So fully data-driven models, there's no way they suffer from curse of dimensionality. That means that in a high-dimensional space, for example, all these different cars that we saw before, in order to describe that variation, you need 50, 60 parameters. All of these points are really far away one from each other. You cannot define a local topology. If you want to define them, and you need to define them for data-driven models, you need millions of realizations. And this is why there's an opportunity for big money, for big capital, because if you have enough money, and if you can spend to make millions of realizations, you automatically create a barrier that no one can step over. So for them, this is an opportunity. It is, from an intellectual point of view, it is probably one of the most stupid things that you can do. But from a business point of view, it's a huge opportunity. The first one who will be able to do that, because they will create such a large database in order to do that, will take it all. And for them, the fact that no one else can do that without all of that money, for them, it's a good point. It is like protecting your IP. You don't do it with a patent, because the patent, it doesn't protect you much. This way, you protect it much more. Okay, here, just to give you an example that it's not just that we really can do these kind of things. For example, on here we have a shock flow about the NASA Common Research Model. You can see, for example, even for shape variants of that airplane, you see, for example, the convergence curve of a reduced order model, the error as a function of the training data, with respect of a deep learning. And you see, for example, what we always said, let's say, in this case, 100 points, you get to a reasonable result that you can dream of with 100 points of a deep learning approach. But, okay. Yeah. Okay. This is what I just said before. What I hope I was able to communicate is that in reality, or let me skip to the next slide. Here, I put it hopefully better. That in reality, reduced order models, in the way that they have been conceived from the very beginning, is probably one of the smartest things that you can do to employ your data. It suffers from two major drawbacks. One is the difficulty to span across different use cases. So it is normally relegated to data just created for one task, and every time you have to regenerate the data and things like that. And of course, industry does not like that, because you have to create the data, then you have to train the model, then you can use it. But now you change something, you have to recreate a data set. So this is something which, in my opinion, needs to be addressed. Because this is the major differentiator with respect to deep learning. In deep learning, you can create a data lake, put everything inside, and exploit it. The other one is, of course, that for now, they're mostly very intrusive methods. I mean, projection methods are more intrusive, collocation methods are a little bit less intrusive. But for now, it is a space, a development space, that from an industrial point of view, it is exclusive to the owners of the codes. For example, we are not, and so it is difficult for us. But it has a major advantage, that it is not or less affected by curse of dimensionality. The amount of data that you need to train a reduced R model, even if you dream of a large project, is orders of magnitude less than with respect to deep learning. On the other side, for deep learning, we saw that you need a huge amount of data to train it. In reality, there are opportunities because, for example, if you think of, rather than learning an entire flow field, you could try to learn small features of that flow field and put them together. Exploit self-similarity and things like that. So there are potentials. But as for now, you need huge amount of data to train these models. And it is an opportunity, rather from a scientific point of view, it is an opportunity for investments. And this is what is happening in this moment. What we have anyhow seen is that reduced order models keep their point in two major domains. One is multidisciplinary simulations and multi-scale optimizations. For example, in this, this is a simulation of this is actually a heat exchanger, which is, it is 3D printed and it is composed of these microchannels. And you can see you have tens of thousands of these microchannels here, there, and it is impossible to simulate it. For example, what is being done is that what is happening is in a single channel is expressed to a reduced order model, and on a macro scale, these reduced order models are glued together through a solver. And as I said, I think the most successful projects on reduced order models up to date is about multidisciplinary and multi-scale projects. Okay, I would like to stop here. I'll be happy to answer any questions, any curiosity. Yeah, and once again, thank you for your time. I hope it was interesting for you. Okay.